Okay, let's start. Let's start. Today I'm going to do a small lesson that is called collisions and impact. Collisions and impact. Then very simple lesson. Definitely your part A, question number 1 will be collisions and impact question. Collision and impact question. And again, this collision part need to do some linear motion questions. Okay, this is very simple one. Write down topic collisions and impact. Collisions and impact. Collisions and impact. This is very simple and important lesson. Okay. Okay. Now you just see this one. You consider small spheres. Small spheres. Usually we can say small spheres just like particles. Particles. Or that can be a sphere. Large sphere. So anyway, when they collide together, we have two different collision type. We have two different collision types. First one we call direct collision. The other one we call oblique collision. Direct collisions and oblique collisions. Under A-levels, we need to analyze only about direct collisions. Direct collisions. Okay. Then we have two different collisions, oblique collision and direct collision. So when you consider two spheres, here consider a sphere. So here it's center of gravity or center. So that is on horizontal surface. So let give velocity u to this center. Therefore velocity, then take another one, another sphere, its velocity along. So here the line joining of centers. Then velocity is along the line joining of the centers. Then when u greater than v, definitely they will collide, no? When u greater than v, definitely they will collide. So you further consider here another particle. Here this is at rest on same plane. So here this has velocity u. So definitely this will collide. Here 1, 2. Now you consider another case. Consider another case. Here two spheres on same plane. So here velocity u, then here opposite direction velocity v. We have two velocities, u and v. Then definitely they will collide, no? Therefore, the velocity is always along the line joining of the centers. Here velocity is always along the line joining of the centers. So here they collide, here they collide, here they collide. This collision we call simple collisions. All these are we call simple collisions. Simple direct collisions. Simple direct collisions. So after the collision, their velocities can be different, no? Their velocity can be different. So we're going to find after collision velocities. We're going to find after collision velocities. So here we have two different theorems. One is called conservation of momentum, you know that one. And the other one we call Newton's law of restitution. Newton's law of restitution. That is new one for you. Okay. Now you consider here particle, its velocity along this, let's say horizontally. Consider another particle somewhere here. Then here center joining line. Here center joining line inclined with the velocity, no? So this collision we call oblique. Oblique collision. Oblique collision. Here center joining line, here velocity inclined to that center joining line. But here this case, velocity is along the center joining line. This line we call line of collision. Here line of collision. Line of collision. Here this is we call line of collision. This is we call line of collision. We call line of collision. Here this case, the center joining line we call line of collision, not this one. Okay. Then velocity along the line of collision we say direct collision. Otherwise it is oblique collision. Oblique collision. Okay. So here we have two theorems. One is conservation of momentum. So here the momentum, you consider as simple m, its velocity u, then momentum we call u times m times u. So momentum is a vector quantity. It's a vector quantity. It has magnitude and direction. Okay, magnitude and direction. So the conservation of momentum says that before collision momentum equal after collision momentum. Before collision momentum equal after collision momentum. Okay. First you sketch this diagram, these diagrams. Okay, you put this on as well. This is oblique collision, and here we call momentum. Momentum, just right. Okay. Now you just write this way. Let two spheres as shown in the figure when the velocities of the spheres are alone the center joining line and when they collide together the collision is said to be direct collision or direct impact. The center joining line is called line of collision. Line of collision. Line of collision. Line of collision. Go to next line and write Let two spheres collide together. When two spheres collide together, let two spheres collide together with the velocities with some inclinations with the center joining line is called an oblique collision. Oblique collision. Put star mark and write down. Always collision happen along the center joining line. Along the center joining line. Okay. Next line, write down. To analyze direct collisions or oblique collisions. To analyze direct collision or an oblique collision. To analyze direct collision or an oblique collision, we use first one, conservation of momentum. Second one, Newton's law of restitution. Newton's law of restitution. Okay. Now you just consider. Here we mainly focus about two sphere collisions, or one sphere and a wall or floor collision. Usually we think about spheres. But there can be different object collisions. But we don't analyze that one for now. Okay, we only consider about sphere collisions. Usually we consider direct collisions, not oblique collisions. So here this one not in our A-level syllabus, but we can analyze that using our basic theorems. But anyway, we only consider about simple collisions. Here these are direct collisions. Here there can be three cases. Here this one, and here this one, and here this one. Face-to-face collision. Here one is at rest, the other one come along that line and collide together. And here same direction, velocities we have, then they collide together. Anyway, we call they are direct collisions. Okay. Now we know moment. Velocity, mass into velocity, no? Mass into velocity. Then you know conservation of momentum. Initial velocity momentum equal after collision momentum. Initial collision momentum equal after collision momentum. Okay. Now you consider here u, here v, u greater than v case. Here before collision. U greater than v case before collision. So here at the collision, so at the collision there will be huge force. We say that one an impulse. At the collision there will be a force. It just look like reaction, but that is not a reaction. Okay. just look like a reaction. Here this is we call an impulse. We call an impulse. So you consider after collision. Here after collision, here say velocities v1 and v2. Here say mass m. Here capital M. Here simple M. Here capital M. Here take this simple direct collision. Take this collision. Okay. Now here after collision. After collision, take your V2. So here there's one important thing, that is here before collision they definitely U greater than V, no? Otherwise they don't collide. So after collision you remember here V2 value greater than V1 value. Here this is important. Previously here simple M velocity greater than capital M velocity, but here after collision capital M velocity greater than simple M velocity. That means relative velocity direction has changed. Relative velocity direction has changed. Here relative velocity u minus v, here relative velocity v2 minus v1. Therefore, definitely here front object velocity will be greater than the previous, the other one. Okay, this is the collision. This is the collision. Then conservation of momentum. Conservation of momentum, we need to use this one along some certain direction. Then here simple M into U plus capital M into V, initial momentum, total momentum. Here after collision total momentum, mv1, you know this one, capital M v2. No? We have two different techniques to find v1 and v2. No? This is one. This is one. Then here final momentum equal initial momentum along same direction. So by conservation of momentum, we consider before collision and after collision, not at the collision. By conservation of momentum, we consider about before collision and after collision. Okay, before collision, after collision, but not at the collision. But we have another formula to analyze at the collision. We have impulse formula. Then by that one we can find this at the collision thing. So this is conservation of momentum. Then further you consider an impulse. An impulse. So impulse means very large force at a small time. So you consider here this mass simple M, so that moves with velocity u. So I'm going to give an impulse I, then due to that one, velocity will change. Say v. Here u change to v. So to change that u velocity to v, we need an impulse. To that instant change, we need an impulse, not a force. Okay. Then you consider F equals ma formula. F equals ma formula. Then say F equal m. A mean v minus u, take that certain time simple t, small time simple t, then cross multiply. Then ft equal mv minus mu. Then ft we call an impulse, we call I. And for this one we say delta mv. Delta mv. So this is our formula, impulse formula, I equal delta mv. I equal delta mv. Okay. Then here momentum difference, final momentum minus initial momentum. Momentum difference, final minus initial. Final momentum minus initial momentum. That is equal momentum difference equal impulse. Okay. To analyze this one at the collision, we can use that formula as well. We can use that formula as well. Later we will see how to do that. Okay. Now you sketch, before that just write down, let two spheres, simple M and capital M. Let two spheres simple M and capital M. with velocities u and v, with velocities u and v, with velocities u and v along same direction as the given figure, as the given figure. The collision occur when u greater than v. The collision occur when u greater than v. The collision occur when u greater than v. Okay. Now you sketch this diagram first. Only this diagram. The other part don't write. Later we will try this one. Just put this one only. Okay. Now with star mark write down conservation of momentum. Conservation of momentum. Conservation of momentum says that the momentum won't change. The momentum, the total momentum won't change. The total momentum won't change along certain direction. Along certain direction when there's no external force. When there's no external force. When there's no external force along that direction. Along that direction. Okay. But at the collision, there will be a large force. There will be a large force. But at the collision, there will be a large force for a small time. For a small time. Which is known as an impulse. Which is known as an impulse. which is known as an impulse. Due to an impulse, due to an impulse, due to an impulse, due to an impulse, instantly, nature of the motion may change. Nature of the motion may change. Nature of the motion may change. Next line. An impulse is a vector quantity. 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 Okay. Now you sketch this diagram and write this thing. Just write that. Here I equal delta mv, momentum difference, final momentum minus initial momentum. Remember that one. Huh? Final minus initial. Final minus initial. Sketch it and write. Okay. Now you see this one. So here this conservation of momentum we can obtain by I equal delta mv as well. By I equal delta mv. So now let I equal delta mv. I equal delta mv. Say you take simple m first. Simple m. So when you take I equal delta mv, we have to get direction like f equals ma. So here I direction simple m this way and here capital M the other way, no? Then I'm going to use simple m here this way. I equal delta mv. I, then I value minus I, no? Then here opposite direction, no? Then minus I. Then I equal here momentum difference. Final minus initial. Here final momentum mv1. Here initial momentum mu. Same direction, no? Then you write here m v1 minus mu. Okay, here first one. Then you take capital M object, use same direction I equal delta mv. Then I alone same direction, then plus. Then I equal here momentum difference, final minus initial, capital mv2 minus capital mv, no? Then here capital mv2 minus capital mv, here 2. Here 1 plus 2, I0, here mv1 mu plus mv2 minus mv. So take initial momentum the other side, then mu plus mv equal mv1 plus mv2. This is conservation of momentum, no? So we can take that using I equal delta mv formula. I equal delta mv formula. Okay, you better to derive that one. You better derive conservation of momentum by I equal delta mv. Okay. First you have to mark I. First you have to mark I. Then you have to put I equal delta mv certain direction. Okay. Thereafter, to cancel this I, we can add. We can add. Okay. Okay. This is very simple question. Okay. Now, when two bodies are collided together, impulse will appear. No? When two bodies collide together, impulse will appear. Okay. Then we can calculate impulse by momentum difference. By momentum difference. Usually impulse we can mark like reaction. We can mark like reaction, but they are not reactions. Okay. Now you consider here sphere collides a floor. So here velocity v, u, let opposite direction after bouncing that velocity v. So there will be instant impulse, say I. We mark this way, I. Then use I equal delta mv, same as simple m. Downward I equal delta mv. Then let's mark upward. Then I equal final momentum mv minus mu. Here mu opposite direction minus mu. Final momentum minus initial momentum. Then here mv plus u. Here this is I now. That is I now. Okay. Then you consider a wall. So here it collides with velocity u. Then it rebounds with velocity v. There will be an impulse, instant impulse for both particle and wall. Then use I equal delta mv. Here this way. Then I equal momentum difference, final momentum minus initial momentum. Here opposite direction minus mu. Then here mu plus v. Mu plus v. Okay. That's how we calculate impulse. Okay. You put that on as well. Here we have to consider directions. Okay, when you take in moment, you have to consider directions. So when you take in I equal delta mv, you have to consider direction as well. Okay. Now you consider this one. Here plane, on that plane, there will be string. It is slack, light inextensible string. So you give velocity u. You give velocity u. So sometimes later it goes to this position. Now it's just about to tot, no? It's just about to tot. Okay. So at this position, instantly velocity will change, say v1. So due to that change, a large tension will appear here. We call that one jerk. That also impulsive force. We call jerk. J, we mark by J. That also impulse. So that along this line, along this string, therefore here v1 velocity, again along string velocity will become same. Therefore this change to v1. It change to v1. Always remember, along string velocities, displacement, accelerations are same. So due to this impulse, this velocity will change, and again this will becomes to v1 again. v1. Okay. So now you consider I equal delta mv. So here mass simple M, let this mass capital M. So here simple M, here capital M. Use I equal delta mv, simple M, here this way, then minus j equals simple M final momentum mv1 minus initial momentum mu, same direction. So capital M, so here opposite no minus, okay. Then this way j equal capital M v1 no, initial velocity 0. Now you add them, here 1, 2, 1 plus 2, j cancel, 0 equal m plus m v1 minus mu. Here v1 equal mu divided by m plus m. Now here the velocity of the system after that jerk, no? Due to that jerk, the velocity will change. Along the strings, there will be same velocities. Okay, take that example. For this case, we can't apply conservation of momentum. Definitely, we have to use I equal delta mv. We have to use I equal delta mv. No conservation of energy possible. No conservation of momentum possible, no? Okay, do it. Okay. Now let's move further. Let's move further. We have to analyze one only thing. Okay. So that is Newton's law of restitution. Then the lesson is finished. Okay. Write down next topic, Newton's law of restitution. Newton's law of restitution. Newton's law of restitution. Okay. Now you see this, Anna. It says that, so there are some collisions now. So some collisions, total kinetic energy will conserve. Those collision we call elastic, perfectly elastic collision. No? If the total kinetic energy will conserve, then it is said perfectly elastic collision. If total kinetic energy loss, then we say that is perfectly inelastic collision. Due to that collision, total kinetic energy loss, then that is perfectly inelastic. So if kinetic energy conserve, then we say perfectly elastic collision. So we consider about some collisions, they are elastic. Sometimes they can be perfectly elastic or inelastic, but usually middle level collisions can happen usually. So that is we call elastic collisions. elastic collisions. Okay. Then to analyze those elastic collision, we consider Newton's law of restitution. It says that relative velocity before collision, after collision, divided by relative velocity before collision that equal to a constant value. That equals to a constant value. For certain objects, that constant won't change. So that constant we usually denote by E. E. This E naught are 2.1, that value not here this one, okay? This is one another constant, E. This E we call coefficient of restitution. Coefficient of restitution, then this E always in between 0 to 1. E always in between 0 to 1. Here can be equal to 0, can be equal to 1. Here E equals 0 we call perfectly inelastic. Here perfectly elastic. Elastic collision. Okay, that is we call Newton's law of restitution. Relative velocity after collision divided by relative velocity before collision is a fraction. So relative velocity before collision usually larger than relative velocity after collision. Therefore, this is a fraction. Perfectly elastic, you remember E value 1, perfectly inelastic E value 0. Usually when you are doing questions, then this E will be given. Coefficient of restitution will be given, or we need to find it. Okay, put that law. Okay, now you see this one. You just see this one. Consider two spheres or two objects, let's say A, B. Velocity same direction, U and V. Then when they move same direction, relative velocity is the velocity difference. Then velocity difference. So you consider velocity of B with respect to A. If you need velocity of B with respect to A, we need to stop A. So to stop this A, you give opposite direction U velocity. Then here this become V minus U. Then the velocity of A with respect to B, you have to stop B, no? You have to stop B. Then to stop B, you give opposite direction V velocity. Then this becomes 0 and this becomes U minus V. That is relative velocity. Anyway, you remember, same direction motion, relative velocity is the velocity difference. Then here relative velocity of A with respect to B, is U minus V. So with respect to B mean stop B. stub B. To stub B, you have to remove this V, then give opposite direction V velocity. This becomes 0, this becomes U minus V due to that change. So here U minus C. Now you consider here B, here U, here A, here this velocity U, this is stationary one. Then relative velocity of A with respect to B. Now here already it is stationary, no? Not moving. Therefore relative velocity here just U. Just U. Here direction, here this way, and here direction, same direction. Now you consider two objects, opposite directions, U, V, here A, here B, opposite directions. Then relative velocity of A with respect to B. Now you have to stop B, no? You have to stop B. Then you have to give opposite direction V. Then this becomes 0, this becomes U plus V, no? Then here relative velocity U plus V. Now you remember that result. So when two objects move same direction, relative velocity is the difference. So when they move opposite direction, then relative velocity become the velocity addition, no? Relative velocity become velocity addition. This is simple theory. This is about relative velocity. Okay, put that note first. Put that note first. Okay. Now you come to this one. Now here these two particles, after this collision, there are two different velocities now, v1 and v2. Then to find those two different velocity, we have two equations, no? So one is known, that is by conservation of momentum we can take that, or otherwise by considering I equal delta v we can derive conservation of momentum. Then finally we can get that equation. Then further we need another equation. So we take Newton's law of restitution. We take Newton's law of restitution. Then it says that relative velocity after collision divided by relative velocity before collision is a fraction. It is constant value, E. Then when you cross multiply, relative velocity after collision equal E times relative velocity before collision, no? So before collision times some fraction equal to after collision. So remember that way. Okay, now let's apply it. Consider this collision. Consider this collision. Now relative velocity after collision. Relative velocity after collision. I told you. So here relative velocity direction will change, no? Here v2 greater than v1. Then here relative velocity after collision, relative velocity before collision, you take these two as positive relative velocities. Then because E positive fraction, then here v1 less than v2, therefore after collision relative velocity you write v2 minus v1. v2 minus v1. Don't write v1 minus v2, okay? We know v2 is greater than v1. Then v2 minus v1 equal E times relative velocity before collision. Here we know u greater than v, therefore same direction velocities, relative velocity u minus v, no? U minus v. This is Newton's law of restitution. Newton's law of restitution. Relative velocity after collision mean v2 minus v1 equal E times relative velocity before collision u minus v. U minus v. Okay. This is we call Newton's law of restitution. Okay. You better to sketch this one and how to write how to apply Newton's law of restitution. So we use Newton's law of restitution along the line of collision. Newton's law of restitution apply along line of collision. along line of collision. Okay, that's how we apply Newton's law of restitution. Then you consider this one. Consider here a flow, particle moves with velocity u, then E given, coefficient of restitution is given between this collision. So usually that coefficient of restitution will be given, or we may need to find. So you consider after collision velocity v. After collision velocity v. Therefore, now we apply Newton's law of restitution. Apply Newton's law of restitution. Then relative velocity after collision. Relative velocity after collision, here v, this is stationary v. Then E times relative velocity before collision. Then before collision relative velocity u. Now here the velocity v equal E times u. So here v value E times u. So when you consider horizontal wall, u after collision velocity take v. So Newton's law of restitution. Now just apply Newton's law of restitution. After collision relative velocity, here this is stationary wall. Therefore relative velocity is v. E times relative velocity before collision, here u. Then you remember, when a particle collides with a floor or a wall or any barrier, then the velocity will be E times u. Now you consider, first mark this one. This is very important results. Important results. V equal EU. Both case V equal EU. Okay. Now further you consider this one. Here inclined plane alpha. So particle moves with velocity u this way. But collision happen along this direction. No? Here velocity u. So when you consider u, here alpha 90 minus alpha, then u cos alpha. Then here after collision velocity u mark perpendicular v1. Then here along the plane v2. Here after collision velocities. Then here collision happen along this line. Then v1 equal, here u cos alpha. No? Then by u cos alpha component collision happen. Then E u cos alpha. Here EU cos alpha. Then v2 equal u sin alpha. Now collision along that surface. Then u sin alpha. Then along the surface, you can resolve. Then perpendicular to the surface. Then initial velocity component u cos alpha. Then u cos alpha multiplied by E. E times u cos alpha. Here inclined plane, for inclined plane. Okay. And you consider here wall, vertical wall. Here this way velocity u, take angle alpha. Then after collision velocity you mark here v1, here v2, v1 and v2. Then v2 will be u cos alpha, no collision along that surface. Then v2 equal u cos alpha, u cos alpha. Then u sin alpha component collide with the wall. Then u sin alpha times e will be this. Then v1 e u sin alpha. That's how collision occur. Okay. Then perpendicular to the wall, velocity component act with the collision. Therefore, multiply that component with e. Then here the after collision velocities. Better to mark that as well. Okay, here u inclination alpha with the wall, then u cos alpha component, no collision along the surface, no? Then u cos alpha remain as it is, but u sin alpha component, here u sin alpha component collide with the wall, then opposite rebounds in velocity eu sin alpha, u sin alpha times e. Here vertical velocity v u, then here perpendicular to the plane velocity component u cos alpha. Then u cos alpha multiplied by e. U cos alpha multiplied by e, that is v1. Then along the surface no collision. Then u sin alpha. U sin alpha remain as it is. That is a slip, no? Okay. Now further you see. Consider here particle collides with this floor. Then velocity u now, here first collision, then rebounds in velocity eu, no? Rebounds in velocity eu. So later it goes like this and again come back with velocity eu. Then second collision will occur. Then thereafter velocity will be again u multiplied by e, no? Then here velocity will be e squared u. Then it goes like this and it comes to flow again. Now its velocity e squared u downward. Then again third collision will occur. Then we have to multiply it again by e, no? Then here now velocity e cube u. It's so on, it moves like this. Then next collision, it goes so on. Then collision won't end. It happen always, repeatedly it happen, but we can see at the end it goes towards equilibrium part, no? So anyway, collision happen like this. So for perfect elastic collision, the collision always happen continuously, like simple harmonic motion, no? Continuously it happen, but this case it goes down. Okay, it is infinite series here. Infinitely it collides, no? Infinitely it will collide. Okay, here you consider here upward u velocity, then downward u. You consider this full motion now. So when you consider VT graph now, now here it is. Here time, velocity, initial velocity u, then under gravity motion it comes to velocity u again. So here time t1, so downward time again t1, no? We know this. So at this position velocity minus u, it collide, then velocity become eu, then eu takes somewhere here. So instantly change the velocity, eu. Now thereafter motion under gravity. So motion under gravity now. Then here parallel lines, alpha parallel lines. Here now it comes to, when it comes to the ground, the velocity now minus eu. Here minus eu. Now second collision will happen. then e squared u velocity, instantly it will change, no? Then instantly velocity e squared u. So instantly you change the velocity. Thereafter it moves, then before collision velocity e squared u, no? Minus e squared u. Then same inclination. Okay, here time t2. Here this time t2. Here this time t3. This time t3. So on it goes, no? So on it goes, VT graph. VT graph. Likewise it goes. Okay, sketch. Okay. Now you see this. Here tan alpha g, no? Tan alpha equal g. G equal u divided by t1. Then t1 equal u over g. Then here t2, again tan alpha g eu over t2. Then t2 eu over g, no? Then tan alpha here g, that is e squared u over t3. Then t3 times e square u divided by g, no? E squared u divided by g. Likewise, you can find time. Then here t1 downward motion t1, then t2 again downward motion t2, t3 downward motion t3, it goes so on. Then let's consider three collisions. So then time, total time, then 2t1, 2t2, 2t3. Here time for three collision. Let's say t3, 1, 2 collision. Time for two collisions. Then here t1, 2t1, t2, 2t2, likewise. Here it is. Then 2 t1 equal u over g, 2 eu over g, 2 e squared u over g. Then you take 2 u over g outside, then it becomes 1 plus e squared. No? Then total time of flight. Now see, total time of flight that happen continuously, no? Up to infinity it goes. Then total time you say t, 2u over g, get the pattern, 1 plus e squared plus e cubed plus e to the power 4, so on, infinite series. You have to take infinite series sum. Here 1 e square, e cube, e to the power 4, it goes on. Then this geometric series. You just remember Sn a times r squared up to a times r to the power n minus 1 geometric series sum. So you know that one geometric series sum, that is a 1 minus r to the power n divided by 1 minus r. Here geometric series. Okay. So let r in between 0 to 1, n goes to infinity. That means infinite series sum. Here r fraction to the power infinity, 0, then a over 1 minus r. This is another important result. Just remember that one. So later we will discuss that one under series lesson. But anyway, you have to remember arithmetic series sum, geometric series sum both. So here geometric series sum first term A, then common ratio R, it goes like that. Number of terms N, then remember A into 1 minus R to the power N over 1 minus R. So when R value fraction 0 to 1 value and number of terms infinity, here fraction to the power infinity, that becomes 0. 0, then final result A over 1 minus R. So now if you take this one, here E mean fraction, no? We know E, coefficient of restitution, 0 to 1 value. Then here fraction, infinite series sum. Then here first term 1, common ratio E. Therefore you take here sum 2U over G, take A over 1 minus R. A mean 1, 1 minus E. Then 2U over G, 1 minus E. Then here the total time taken until it becomes to rest. Okay, total time taken. So this is important resource, better note that one. Okay, complete that question, complete that. Complete. Time for 3 collisions. Time for 3 collisions. Okay. Now you consider this one. Then collision analysis very simple. Then after that we need to consider about linear motion or something else. So collision analysis very simple. Usually we consider only about sphere collision with a wall, sphere collision with a floor, or two sphere collisions and so on. That's it. No any other thing. Okay. Then after that we have to do further analysis according with after collision. Okay. Now you consider here floor, here there's a ceiling. Here take this side simple edge. So I'm going to project a particle vertically upward u velocity. Okay, just consider that can reach this position. So this velocity enough to reach this position. So you take here A, take here B. Then you consider upward b squared equal u squared plus 2as. Then take here velocity v1. Then v1 square u square minus 2gh. Okay. Then v1 equal u square minus 2gh root. So you consider velocity u. Here initial velocity u given. Let u greater than 2gh root. Then definitely one collision will occur. No? So if u greater than 2gh root, definitely one collision occur and with the ceiling. So here now it collide. No? Then after collision, its motion will be downward EV1. No? EV1. You take here this collision, coefficient of restitution E, EV1 now. So now it comes to here this position. Yeah, when you consider first collision, here the velocity, similar use v equal u plus at. then V1 u minus GT1. Then by this you can take T1 value, no? Take T1. V1 equal u squared minus 2GH root minus u divided by G. Here T1 value. That is T1 value. Divided by G. Okay. Then EV1 downward. Now use downward. V squared equal u squared plus 2as further collision, further motion. Then take here velocity V2. Then V2 square equal u square mean E1, EV1 square 2as plus 2GH now. Then V2 equal E squared V1 squared, V1 square u squared minus 2GH plus 2GH. Again whole thing root, no? Now its velocity E square u square plus 2GH 1 plus E square, 1 minus E square. Here the velocity now before the collision. After collision, velocity now you take here E dash. Here this collision take E dash. Then here this will be E dash V2, no? E dash V2. Therefore V2 you can write with E dash V2 you can easily write, no? E dash V2. Likewise you can consider the analysis. So anyway this collision knowledge need only for collision. Further part we can do different techniques. So linear motion, further part under gravity motion. Only collision we analyze using that Newton's law or conservation of momentum. Okay. Put that example as well. No need to do all the things, but just write how to analyze that. Just enough. You divide by G. Okay. Here time sign somewhat different, no? U minus V1. T1 equal U minus V1 divided by G. U minus V1 divided by G. Now you write this question, just write. Consider the following two spheres collision as the given figure. Consider the following two sphere collisions as the given figure. Consider the following two sphere collisions as the given figure. The coefficient of restitution is E. The coefficient of restitution is E, simple E. Find after collision velocities. Find after collision velocities. Find after collision velocities. Okay. Now you better do with me. Better do with me. Here first one, Here mass simple limb, here stationary body mass simple limb, say AB, it comes with velocity u and collides together. Then after collision you mark velocities, you do with me. Here masses m and m, take velocity v1, v2. You always better to mark v1, v2 velocities usual way. Then let's apply conservation of momentum. Later we change this one. We will change later conservation of momentum to I equal delta m. But for now, you apply conservation of momentum and Newton's law only. Then here, mu equal mv1 plus mv2. Then v1 plus v2 equal u, first relation. Then Newton's law, apply Newton's law. Then relative velocity after collision, v2 minus v1 equal e times relative velocity before collision. Now we have two formulas, two equations. Then find v1 and v2. 1 plus 2, 2v2, u plus eu. Then v2 equal u, 1 plus e divided by 2. Then 1 minus 2, similarly you obtain the v1. 2v1, u minus eu. Then v1 equal u, 1 minus e divided by 2. Likewise, you can easily find. No? You apply conservation of momentum and Newton's law of restitution. That's it. Here u plus minus e1 divided by 2. Okay. Do soon. Do soon. Okay. Now you take another one. Here, second case, velocity u, opposite direction velocity v, mass simple limb, take AB. Do with me. Here after collision velocity take v1, v2. Here AB, simple limb, v1, v2. Now conservation of momentum, mu minus mv equal mv1 plus mv2. Then v1 plus v2 equal u minus v. You always better to mark v1, v2 same direction. So here second body is here, first body A collides with B now. Then here A can becomes to rest or it can move opposite direction. Okay. Then three cases happen for A, but for B definitely there's only one case. It moves away, no? Okay. Now apply Newton's law. Relative velocity after collision, v2 minus v1 equal relative velocity before collision, face to face, u plus v. Now that's enough, no? 1 and 2. Now 1 plus 2, 2v2, u minus v, eu plus v. Then v2, u 1 plus e, v e minus 1. Divide by 2. Then 1 minus 2, 2v1, u minus v, u plus v. 1 minus e, u plus minus 1 plus e, v divide by 2. Divide by 2. Okay. Here 1 minus e, u, here v, this is minus, no? That is our velocity now. Okay, completed. So anyway, these two important, conservation of momentum and Newton's law, that is the theorem. After your simplification, you can do your way. Okay, do it. Okay. Then those are direct collisions. Those are direct collisions. You just mark after collision velocity is v1, v2, then apply conservation of momentum and Newton's law of distribution. After that, you can simplify the equations. Okay. Okay. Okay, let's do further more questions. Okay, do with me. Do with me. Here, third one. A, B, U, V, M, M. After collision velocity v1, v2 masses same. Same masses. Do with me. Conservation of momentum. Mu, Mu, mv1, mv2. v1 plus v2 equal 2u. Then Newton's law of distribution, v2 minus v1 equal E u minus v. Here v2 minus v1 equal E u minus v. Here this relative velocity take positive values. Then we can solve simultaneous equations. 1 plus 2, 2v2, 2u, E u minus v. Then v2, here not u plus v, no? Here u plus v. U plus v. Then u plus v. 1 plus e. 1 minus e v. Divide by 2. 1 minus 2, 2v1, u plus v minus e, u minus v. Then v1, u1 minus e, v 1 plus e divided by 2. Likewise, you can get, na? Okay. Then masses can be different, velocities can be different, but the method fixed. The masses can be different, velocities can be different, the method is fixed. Then very simple part. Okay, take linear motion to 2013 one we done before, 2013 one. So just mark it, 2013 one previously we done. So that also connected with collision. So linear motion, we need to think about that E times U relation. When a particle collides with a floor or wall, then rebounds in velocity EU, no? Thereafter we can proceed. 2013 we done. Then read 2015 and start. Read 2015 and you start it. 2015 A-level question. Okay, just start it. 2015 A-level question. (2015) two particles PQ are simultaneously projected with vertically upwards with speed u and u over root 2. here particle P, velocity u, here particle q, velocity u over root 2. So here the ceiling, height given, u squared over 4g given. The coefficient of restitution between ceiling and the particle P, 1 over root 2. Find the speed of the particle P just before strike. Then take here V1. Then particle P, use upward, V squared equal U squared plus 2AS. Then V 1 square, U square minus 2G H. H given U squared over 4G. Then here U over root 2. V1 value U over root 2 just before the collision. Just before the ceiling, collide with the ceiling. And time t1. Again particle P, use upward, V equal U plus AT, V equal U over root 2, initial velocity U, G, T1. T1 subject, U root 2 minus 1 over root 2, G. Here subject T1, root 2 minus 1, that is it. Show that the particle P returns to its point of projection with speed. Okay, now it's collides, no? Then rebounds in velocity EV1. E given 1 over root 2, V1, U over root 2, that is U. Then again use downward, V squared plus U squared plus 2AS. Then you take velocity, again V2. Then V2 square equal U square plus 2G, here U squared over 4G. Then root 3 divided by 2. V square equal U squared minus 2G U squared of 4G. Then U squared of 4, U squared of 2. Okay, U over root 2. Then coefficient of restitution 1 over root 2. Here U squared U over 2, no? U over 2. Here U squared over 4, U squared over 2. Then V2 root 3 U over 2. Here V2 when it comes to ground again. When it's come to the ground again. So that the particle Q just reached the ceiling. So now you consider Q particle. Q particle upward, use V squared equal U squared plus 2AS. Then say V3 U over root 2 square 2GH U squared over 4G. Then that value 0. Therefore, Q just reach the ceiling. Just reach the ceiling. Okay. Then we need to find time now. Use upward, V equal U plus AT. Then corresponding time, velocity 0, U over root 2. 2g v equal u plus 8t gt2, then t2 equal u over root 2g, here corresponding time. Okay, continue. So here we need to analyze only about undergravity motion. Undergravity motion. Here is still not saying about VT graph as well. Then later it says that we have to sketch VT graph later, but for now, up to this, no need to sketch VT graph. Okay, do up to that. Sketch VT graph. Here time velocity, first particle P, initial velocity U. So motion under gravity. Motion under gravity, when it comes to the ceiling, its velocity now v1. v1 u over root 2. Then mark it u over root 2. Let's mark somewhere here. Then at this point, instantly its velocity change due to that collision. That velocity become u over 2. Then u over 2 somewhere here. U over 2. Then its motion downward now. Downward motion. Then angle alpha. Then downward motion. Alpha. Here particle P. Instantly velocity change due to that collision, and it goes under gravity. Then same time, particle Q start with velocity u over root 2. U over root 2, no? Then same level here, you start, move under gravity, same line parallel to all previous lines. So at this point, here capital T1, then here this one T1, then T2 time here it is. So when it reached the maximum height, it just reached the ceiling. So here the maximum height T2. It goes opposite direction now. No collision at this point. Then here T2. Here Q. Same inclination alpha. Now that is VT graph for both motions. Using the velocity time graph, show that the instant when P strikes the ceiling, Q is at a vertical distance below the ceiling. So when P strikes the ceiling, here it is, here this level, then Q height is this, from the ground level. No? So when particle P hit the ceiling at this point, then second particle Q, it moving upward. No? It moving upward. Then at this time, bounded area we call the height. That is the height now. You mark here velocity v4. Let's mark v. Then here alpha. Tan alpha equal g u over root 2 minus v divide by here time t1. Then you find v velocity, t1 equal here u root 2 minus 1 over root 2 g. Then gt1 u root 2 minus 1 over root 2 u over root 2 minus v. Simplify here. Here u minus u over root 2 equal u over root 2 minus v. V equal here root 2 minus 1 times u. Here v1 value, here 2 u over root 2 minus u. Okay, that is the velocity. Then required height, here when it hits this ceiling, then q particle somewhere here, then we got this one, then we need this one, no? Then maximum height, this height u squared over 4g, you subtract that one. Then distance of q below the ceiling, u squared over 4g, distance between u squared over 4g, distance between floor and the ceiling. Okay, subtract here this shaded area, half into t1 into u over root 2 plus e v. Now you simplify this, u squared over 4g 1 over 2 t1 u root 2 minus 1 over root 2g u plus root 2 minus 1 times root 2 u divided by root 2. Okay, now just simplify that one. Then that will be your answer. Now simplify u squared over 4g minus, here again u squared over 4g root 2 minus 1, and here 2 3 minus root 2. Then take u squared over 4g outside, 1 minus here 3 root 2. 3 root 2 minus 2 minus 3 plus root 2. Further simplify, u squared over 4g, here 2, 3, 5, 4, 6, 6, 3, 4, here it is. Now further we can simplify, u squared over 2g divided by 2, 3 minus 2 root 2. Here further we can write u squared over 2g root 2 minus 1 squared. Here 3 minus 2 root 2 will be root 2 minus 1 squared. Okay. Continue and complete. Okay. Now let's do further questions. Now linear motion and collision application with linear motion already done now. That is completed now. So you have to think only about collision, after collision velocity, thereafter linear motion part analysis. Okay. You try these questions. Okay. Okay. You try this question, find after collision velocities. You just find after collision velocities for these cases. Take time. Check your answers. First one, after collision velocity v1, v2, m2m. Here, conservation of momentum mu, mv1, 2mv2. v1 plus 2v2 equal u. Newton's law, relative velocity after collision v2 minus v1 equal e. E mean half, no? Half relative velocity u. Now we can find v1, v2, no? 3v2 u plus u over 2. Then v2 equal u over 2. Then you can find the other one, no? Okay. Then second case, take velocities again, v1, v2, mass 2m, m. Conservation of momentum 2mu, mu over 2, 2mv1, mv2, mv2. You always mark after collision velocities general way, okay? Just mark general way. Then Newton's law, v2 minus, before that simplify, 2v1 plus v2 for 5 u over 2. Then Newton's law of restitution, v2 minus v1 equal 1/3, e mean 1/3, u minus u over 2, u over 6, v2 minus v1. Then 1 minus 2, 3v1, 5u over 2, u over 6. Then v1, here 15, 14, 14u over 18. Okay, na? v1, 14u over 18. 15, 14, 6, 18. Okay. One velocity enough, huh? Then for Newton's law, mass not applicable, no? Mass won't applicable. Therefore, only conservation of momentum, we have to think about masses. All the other cases, no worries about masses, no? Then that is question number 2. Okay, then question number 3. Question number 3. Mark here v1, v2, 2m, m. Then conservation of momentum 2m times 2u, m times u, 2m v1, m v2, 2v1 plus v2, 3u, 4 minus 1, 3u. Then Newton's law, v2 minus v1 equal e mean 1, perfectly elastic collision, relative velocity 2u plus u, say opposite directions. Then v2 minus v1 equal 3u. Then 1 minus 2, 3v1 equals 0. v1 becomes 0 now. Then you can find the other, no? Then this will becomes to rest. That comes to rest, no? That is third one. Okay, then last one, fourth one. Then mark forces. Here m, v1, 2m, v2. Then conservation of momentum, m times 3u, 2m times u, mv1, 2mv2, v1 plus 2v2, 5u. Newton's law, v2 minus v1 equal e, 1/3, relative velocity 3u minus u. Then v2 minus v1, 2u over 3. then 1 plus 2, 3v2, 5u, 2u over 3. Then v2 value 15, 17u over 9. No? 17u over 9. Okay, here you need to practice only how to apply Newton's law, then conservation of momentum generally, then practice how to apply Newton's law. Thereafter, after collision, velocities we can obtain. Thereafter, further analysis we can do. Okay, complete. Now with that one, you see this. Just see this. Now you consider here particle of mass simple m and impulse given I, velocity change u to v. Velocity change u to v. So if you use I equal delta mv, then I equal m u minus mv. No? This is I. Then let's say energy difference here. Here kinetic energy difference. For absorbance, half mv square minus half mu square. No? Then half m v square minus u square. M v minus u, v plus u. Then for this part you can put I, no? Momentum difference. 1 over 2 I u plus v. Here kinetic energy difference you can write by this equation, half times I times u plus v. Half times I times u plus v. Okay. Then if you get positive value, if delta E positive, then energy absorbed. Then delta E equals 0, no kinetic energy loss. Here delta E less than 0. So when delta E less than 0, then final energy less than initial one. Then here energy loss. Now here kinetic energy loss. Kinetic energy loss. Therefore, kinetic energy loss equal minus delta E, then half times minus half times K times U plus V is the kinetic energy loss. Kinetic energy loss. Then usual kinetic energy difference half times I times U plus V. Then loss, here absorb, no? Here absorbance because of I. Then if we have loss, if you need to find loss, then you take minus value of that. Then here this will be kinetic energy loss. Okay, put that one. Here mv minus mu. MV minus MU. Okay, then that's all about linear motion and collision part. Okay, linear motion and collision part, that's all. So later we can do past paper questions and collisions, then very simple thing that one. Anyway, next week we can start relative motion part, relative motion part, relative velocity, relative acceleration.